Hello everyone, my name is Preetham Kormukar. I'm a PhD student at the Robotic Vision Lab at the University of Texas at Arlington. Welcome to the presentation of our paper, Secrets of Edge-Informed Contrast Maximization for Event-Based Vision. Here is an outline of today's presentation. In the introduction section, we will briefly introduce event-based cameras, event optical flow, and our motivation and contributions. In the method section, we'll go over the details of our problem setting and our solutions. Next, we'll acknowledge the challenges that come with real-world datasets, and finally, present our results and conclusion. Event-based cameras are novel sensors that only measure motion in the scene. They offer several advantages, including high temporal resolution, low latency, low bandwidth, and low power requirements, and high dynamic range. As shown in the video, standard cameras produce frames at regular intervals of time. In contrast, event cameras output asynchronous events measuring per pixel brightness changes. These events are temporally dense, spatially sparse, and encode scene motion, making them particularly useful for optical flow estimation. The existing literature on event optical flow can be broadly categorized into model-based approaches and learning-based approaches. Model-based approaches include plane fitting, block matching, warp-based alignment techniques that adapt Lucas-Conade style methods to event representations, and contrast maximization, which is a technique unique to event data, where motion trajectories are estimated by maximizing the contrast of the image of accumulated warped events. Learning-based approaches often adopt frame or voxel-based learning architectures. These methods rarely exploit the inherent working principles of event cameras. Prominent examples include eRaft and EVFlowNet. Event cameras excel at rapidly capturing moving edges. When events are accumulated on 2D spatial grids, edges can appear smeared, obscuring the spatial structure. Contrast maximization can reverse this effect by compensating for motion. However, CM often suffers from issues such as event collapse, which can be mitigated through recently introduced multireference techniques. Nevertheless, the framework remains incomplete. Our hypothesis is that under optimal warp, the image of accumulated events is not only sharp, but also exhibits strong spatial correlation with its corresponding edge image. Our key contributions are as follows. We extend the CM framework in a model-based setting by simultaneously maximizing contrast and event edge correlation. We refine multiscale and multireference techniques to incorporate our novel bi-modal objective. We develop sophisticated sequential processing strategies to improve convergence and enhance performance. Our evaluation establishes new benchmarks on event optical flow across multiple real-world datasets. Our bi-modal CM method accepts both events and edges as inputs. Dense flow parameters are optimized to achieve both high contrast and high correlation with edge images. As illustrated, the left figure shows a volume of events and edge images as inputs. The right figure demonstrates how optimized motion parameters enhance both sharpness and correlation. To extract edges from image frames, we apply a series of transformations including denoising, histogram equalization, sharpening, bilateral filtering, canny edge detection, and Gaussian blurring. The resulting edges are directly used in our framework. We employ a linear warping model. Theta represents a 2D velocity associated with each pixel as expressed in equation 1. The image of warped events, IWE, is obtained by accumulating events over the image plane as shown in equation 2. The Dirac delta in equation 2 is approximated by a Gaussian kernel. In our implementation, the contrast objective is defined as the mean gradient magnitude of the IWE as shown in equation 3. And the correlation objective is defined as the mean squared error between the IWE and the edge image as depicted in equation 4. Both IWE and the edge image are pre-normalized to a new unit range. Contrast and correlation energies are accumulated over multiple frames and reference times, as shown in equation 5 and 6. As expressed in equation 7, our final objective function comprises of a contrast term, a correlation term, and a regularization term. We optimize theta using the BFGS solver available through the JAX framework. We employ a multiscale processing strategy. We refer to the aggregation with preceding iterations as the handover. As shown in the left figure, our pyramidal scheme progresses through the coarsest to the finest scale. At each level, we first perform contrast correlation maximization, then a handover operation with previous parameters, and finally upscaling to initialize the next pyramid level. The video on the right demonstrates our framework in action across 5 pyramid levels. The 3 columns depict the current, preceding, and aggregated parameters at each level. We evaluated our framework on multiple real-world datasets such as MVSEC and DSEC. However, imperfect ground truth and misalignment issues poses significant challenges. In the MVSEC dataset, our method produces sharper IWEs compared to those derived from ground truth flow. In the DSEC dataset, rectification artifacts and registration artifacts, particularly at points near the camera, are observed. Despite these challenges, as can be seen, our method consistently yields sharp IWEs. Additionally, we note that accuracy evaluations on the DSEC benchmark can be misleading due to unavailable ground truth. Note that the periphery of the visual field has dynamic scene points that generate a lot of events. However, the ground truth is either sparse or unavailable in these regions. Therefore, good flow estimations in these regions will not be accounted by the benchmark evaluation. Our method produces sharp IWE across all regions in the image plane. Here are some qualitative results of our method for MVSEC dataset. And here are some qualitative results of our method for ECD and DSEC datasets. Our method achieves state-of-the-art performance on the MVSEC dataset, outperforming model-based and learning-based approaches. The table on the right demonstrates superior sharpness across all datasets. We have additionally performed an ablation study on our multiscale and handover scheme. We evaluated 3 handover strategies. In the first strategy, we solved the handover weights for all pyramid levels. In the second, we fixed the handover weights for all pyramid levels. And in the third, we used a hybrid combination of solved and fixed weights. As shown in the table below, the hybrid strategy performed the best. Here is a visualization of our framework in action. The top row shows the inputs, including frame event overlays and 0 warped events. The bottom row depicts the predicted event optical flow and the optimally warped events. In this work, we introduced a bi-modal extension for CM that estimates event optical flow using both events and frames. We developed advanced multiscale handover strategies. Our method achieved superior sharpness and competitive accuracy across multiple real-world datasets and benchmarks. Thank you for your attention. For more details, please visit us at the poster session and/or read our paper. Thank you.